Alright, so in this video we're going to go over equilibrium and how to solve some of the basic equilibrium problems. So in equilibrium, um, the forward reaction and the reverse reaction are going at the same rate. So basically as your reaction starts, you should start off with all reactants, and the reaction is going to move forward and make products. And then we're going to get to a point where the reaction actually goes backwards to make some reactants. So at equilibrium, the reverse reaction and the forward reaction, the rate at which you're making products is going to be equal to the same rate that you're going to be making reactants. Now, this does not mean that they're at the same concentration. It means that the rate at which I'm making the products is the same as the rate that I'm making the reactants. So when I look at this graph right here, I have concentration on the y-axis and time right here. So as the reaction starts, I'm starting with all reactants, so it's starting at a high concentration, and then I'm moving forward to make more products. So as this line goes down, the product line is going up because I'm increasing my concentration. Well, in this particular reaction, my concentration ends with more products than my reactants. So we would say that this is a product favored reaction. Well, if I look at this one right here, I'm starting with all reactants, 0 products, so I'm going forward and I'm making products. So as my reactants decrease, my products increase, but at the end I actually have more reactants than I'd have products. So it's not that the concentrations are equal, it's that the rate at which I'm making both the reactants and products is going to be equal. So this would actually be a reactant favored reaction. So with equilibrium, if it is a product favored reaction, that means that the equilibrium constant is going to be greater than 1. So if K is greater than 1, then that means I'm going to be making a lot of products. If my equilibrium constant is less than 1, I'm going to be not making as many products, and I'm going to be I will have more reactants at the end. So equilibrium, Kc deals with concentrations, Kp deals with partial pressures, so gases only. We never include solids or liquids into either of these. And we also have Ksp, which we'll go over later, and then Ka and Kb, but right now let's just deal with Kc and Kp. So anytime that I'm looking at a reaction, K is equal to the concentration of my products raised to the power of its coefficient divided by the reactants raised to the power of its coefficients. And if I were dealing with Kp, I would have partial pressures of each thing raised again to its power as well. It would just, instead of concentrations, I would have the partial pressures, and that's it. All right, so if you're given a K value, sometimes they might ask you for the K value if you happen to reverse the reaction, if the reaction changes a little bit. So basically, if you manipulate the equation, you can manipulate K to get the new K. So if I were to multiply that reaction, I'm going to take K to that power. If the reaction is reversed, I'm going to take the inverse, so 1 over what K is. Now, if you could also be given multiple reactions and basically solve it like Hess's law, and then at the end you're going to multiply the K values. So in Hess's law, we just simply add up the delta H's. With K, you would have to multiply them together. All right, so let's look at an example of this. So if I have this reaction, K is equal to this. Well, what is the K if I have this reaction? Well, if I look at this, this is exactly the opposite of what this is. So basically, I flipped this reaction to make this one. Well, what I'm going to do here is I'm going to take the inverse of that. So I'm going to take 1 over my K value. And if I do that, I'm going to get 333. That is my new K value if I reverse the reaction. So I'm not making it negative. K should always be a positive number. I'm going to take the inverse of it. All right, so now let's look at this one. So for this one, well, if I compare to this one, well, first of all, it's flipped. So I would have to be this. And also, it's multiplied by 2. Well, I'm not going to multiply it by 2. I'm going to take it to the power of 2. So if I were to do that, so 1 divided by 3.0 times 10 to the negative third squared this is what I'm going to get for my new K. So I can write it. Okay, so for my new K, when I do this, I'm going to get 1, 1, 1, 1, 1, 1. All right, so basically 1.1 times 10 to the fifth power. That is my new K value. So anytime that we're manipulating the equation, we can manipulate and get a new K value as well. All right, so now K is the equilibrium constant. That will never change. The only thing that changes K is going to be temperature. Now, if K is greater than 1, then the reaction is product favored. So I'm going to make a lot of products. If K is less than 1, the reaction is reactant favored, and I'm not going to make as many products. If K is equal to 1, the concentration will be pretty much the same. The reactants and the products are going to be equally favored. Now, Q is when I measure the concentration or the pressure at any point in the reaction. So it's not necessarily at equilibrium. Now, if Q is greater than K, that means that, well, if I look at the expression, K is equal to products divided by reactants. Well, so is Q. So Q is equal to the products divided by the reactants. So if Q is less than K, that means the number is too small. So if the number is too small, then the top number is too small. So if it's less than K, it's going to be that the top number is too small. So I need to make more products. So the reaction is going to shift to the product side. So basically, if I don't have enough products, the reaction will continue to make products until Q is equal to K again. When Q is equal to K, we're at equilibrium. Well, if Q is greater than K, then that means that the number is too big. That means that the bottom number is too small. So if the bottom number is too small, that means I'm going to go back and make more reactants. So the reaction is going to shift to the reactant side. And so this is going to be important if you're trying to decide if a reaction is going to shift to the product side or the reactant side. And so if you are answering an FRQ and it's asking, okay, which side is the reaction going to shift to, the reactant side or the product side, you're going to say which side, and then you're going to answer using Q in your answer. You need to make sure you address the issue of Q being less than K or greater than K. All right, so let's do some practice problems. Okay, so it gives us the equilibrium concentrations for each thing, and then it's asking for the K value. All right, so the first thing I'm going to do, I'm going to write out the K expression. So the Kc is equal to products over reactants. So H2 to the power of 1 times I2 to the power of 1 divided by Hi to the power of 2. All right, so now, well, it gives me all these values, so I just simply plug it in and solve for it. So H2 is 6.33 times 10 to the negative fourth I2 is 1.23 times 10 to the negative third. And then HI, but HI squared, times 10 to the negative second squared. Don't forget the squared, which is why it's always good to write it out first. And then if you plug it in and solve, you're going to get 0.00125. Also, K does not have any unit, so we don't have units on K. All right, so let's look at another one. All right, so a different type of problem can be like this one. I have 1 mole of H2, 1 mole of S2 placed in a 1 liter flask at 900 Kelvin. It gives us the reaction. When equilibrium is achieved, 0.75 moles of H2S has formed. Okay, so in the last problem, it gave us the equilibrium concentrations. This one, it's giving us the concentration before the reaction starts, and then also one equilibrium value. So let's go ahead, let's look at the K expression. So Kc is equal to H2S to the second divided by H2 to the second and S2 to the first. And also, they should have the states of matter here. They don't. Everything here is a gas. So you are either going to be looking at, if you're writing Kc or Kp, remember you don't include solids or liquids. So normally they're going to have these states of matter written there. All right, so let's do an ice table. So we're going to write out our reaction. And the ice is initial, change, and equilibrium. So initially, I have 1 mole of H2, and it's per liter, so I don't have to worry about the volume. 1 divided by 1 would just be 1 mole per liter. And again, S2 would be 1. Well, at the beginning of the reaction, I have reactants. I should have 0 products. All right, so since I have 0 products, that means I'm going to be creating products in the beginning. So I'm going to be adding some value. Well, I'm going to be adding 2x because it's got a coefficient of 2 there. So, and because I'm going to be making products, I'm going to be using reactants, so I'm subtracting. So minus 1x minus 2x because of the coefficient here. So 1 minus 2x, 1 minus x, and then 2x. So basically combine the I with a C, and then that's what you're going to get. These are the equilibrium concentrations. So it also tells us, though, that when equilibrium is achieved, 0.75, and this is not H2O, this is H2S, 0.75 moles of H2S has formed. Well, that's their concentration at equilibrium. So if it gives you initial concentrations and 1 equilibrium concentration, you need to figure out what X is so you can get the concentration of everything at equilibrium and then solve for Kc. So 2x, well then X should be 0.375. So now with these little mini equations, I can go back and solve for the equilibrium concentration. Remember, this is the equilibrium concentration here, not this. Okay, so 1 minus 0.375 would give me 0.625. And then 1 minus 2 times 0.375 would give me 0.25. Okay, so now I have the equilibrium concentration of all 3 things. I can plug it into my K expression. So Kc is equal to H2S, which is not what X is, it's 0.75. Oh. So it's 0.75 squared. Don't forget to do that. That's why you should write out your K expression first. H2 is 0.25. Square that. And 0.625 is S2. So once you solve for this, you should get 14.4. So this K is larger than 1. It's going to be very product favored here. I should only have a very small amount of reactants at this point. All right, so when 1 mole of N2O4 at an equilibrium pressure of 3 atmospheres is 50% dissociated, what is Kp? Okay, so first thing, okay, these are both gases. Let's write out the Kp expression. So Kp is going to be equal to, we're only going to include gases here, products over reactants, so it's going to be the partial pressure of NO2 squared divided by the partial pressure of N2O4 to the first. All right, so in order to get Kp, I have to have the partial pressure of this and the partial pressure of this. Well, it gives me an equilibrium pressure of 3 atmospheres. This is not the partial pressure of this or this. It is telling me the total pressure at equilibrium is 3 atmospheres. All right, so I know that at equilibrium, my total pressure is 3 atmospheres. Well, it also tells me that I'm starting off with 1 mole of my reactant, and it's 50% dissociated. Okay. The trick here is that some people would probably be like, oh, it's 50% dissociated, so that means that the partial pressure of each of these things is 1.5. That's not true. Okay, you have to be very careful about how they word some of these things. So we actually need to find the partial pressure, but we can't just say it's 50% of 1 or of 3. That's not going to give you the partial pressure, because the thing is, when this disassociates, this makes 2 of these, not just 1. So what we can do is we can find the number of moles of each of these things at equilibrium, and then we can get the mole fraction and multiply that by 3. So anytime that we're looking for partial pressure, this goes back to Dalton's law. If we have the partial pressures of all the gases, we can add those up to get the total pressure. But if you're not given at least one of these pressures, what you could do is you could take the mole fraction, and then multiply that by the total pressure. So what we need to do is we need to figure out how many moles we have of N2O4 we have at equilibrium, and then also NO2. So that's what we're going to do. We're going to set up an ice table, and we're going to solve for how many moles we have of each thing. Okay, so we're going to do an ice table. All right, so initially we have 1 mole of this. We should have 0 moles of my products. So I'm making products, I'm going to be adding. So plus 2x because of the coefficient, minus x here. So at equilibrium it should be 1 minus x and then 2x. Well, I do know something. I know that 50% of this will decompose. So if 50% is what's changing, x is going to be 50% of what we started with. So I'm starting with 1 mole, so 50% of that should be 0.5. So x is actually going to be 0.5. Okay, so now let's solve to figure out how many moles I have of each thing. So 1 minus the half that decomposed should just be 0.5. I should have 0.5 left over. Well, 2 times my 0.5 would give me 1. So I'm actually going to have 1 mole. And really, just if you think about it, well, it said 50% of it decomposed. Well, 1 mole would be, 50% of that would be 0.5. Well, I'm going to make 2 moles of this for every 1 mole that decomposes. Well, I only decomposed half of it, So half times 2 would be 1. So that means that I have 0.25 moles of this and 1 mole of this. So now I can get my mole fraction. So that's going to be my moles of each thing divided by the total moles. Well, total moles should be 1.5. So 0.5 divided by 1.5, and then I'm going to multiply it by the total pressure of 3. So that's going to give me 0.99 here. And really, if this was not an FRQ, I would just round this to 1. All right, and then for the NO2, 1 divided by 1.5, moles of this divided by total moles times 3, the total pressure, would give me 1.98. So that's close to 2. All right, so now I have my partial pressures of both. So now I can plug it back into the K expression and solve. So P, the partial pressure of NO2, is 2 to the second. Don't forget that. That's why you write the expression out. Divided by NO2, 1. So my Kp is going to be equal to 4. All right, so given the following reaction at this temperature, determine the equilibrium partial pressures of all the species if 0.5 atmospheres of chlorine is present initially, and gives you the K value. Okay, so in this problem, we're not solving for K, we're going to be solving for the partial pressures of everything at equilibrium. So it is going to be an ice table problem, but let's go ahead and write out the K expression. So we're dealing with Kp. So Kp is equal to the partial pressure of chlorine to the second divided by the partial pressure of Cl2 to the first. Okay. So now let's go ahead and write out our ice table. All right, so initially chlorine is 0.5 atmospheres. So we're dealing with partial pressures here. And then this is our reactant, so that should be 0. So we're going to be making our product, so plus 2x minus x here. So 0.5 minus x, and then 2x is what I have here. All right, so it doesn't give me any partial pressures at equilibrium, so I need to solve for those partial pressures. But I have K, so I can do that. So now I can just plug everything into the K expression. So K is equal to 1.13 times 10 to the negative fourth. That's equal to the partial pressure of Cl, which is 2x squared, divided by the partial pressure of chlorine, which is 0.5 minus x. Well, hey, this x is very, very small. So this K is small, so we can get rid of this. So anytime that we have a small K value, we can approximate, which means I can get rid of any plus x's or minus x's. I can't get rid of all of the x's, but just the ones I'm adding or subtracting. Okay, so now this is what I have. 1.13 times 10 to the negative fourth is equal to 2x squared. Please, please, please do not forget to take everything in here to the power of 2, which means it's actually 4x squared divided by 0.5. All right, so if we go through and solve this, x is going to be equal to 0.00374. All right, so now I have x. That's not my final answer, though, because now I need to go back and actually solve for the equilibrium pressures. So 2 times 0.00374. All right, will give me 0.00748. Then 0.5 minus 0.00374. All right. So that's going to give me 0.496. All right, so those are my partial pressures at that temperature.